So here we go. So again, what we're talking about today, one-sided limits. And we've basically been talking about this idea already, the idea of approaching, when you take the limit as x approaches c, approaching both from the left side of c, values less than c, and approaching from the right-hand side of c, values greater than c, right? So the idea of a one-sided limit is not necessarily foreign, but we just haven't officially covered it yet. But now we are. So the limit from the right, which I'll put in quotes there, limit from the right means that x approaches c from values that are greater than c. Greater than c, right? Because that's from the right, right? On the right-hand side of c, if you think about a number line, right, to the right of c, on the right-hand side of c on the number line, those values are greater than c, all right? You have to be a little bit careful when you're thinking about this too, especially when it deals with negatives, right? When it comes to a positive, let's say positive 2, right? Numbers to the right of 2 on the number line would be 3, but also 4, but really 2.01, 2.001, 2.0001, so on and so forth. When it comes to negatives, though, you need to be a little more careful. We're talking about -2, okay, -2. To the right of -2 is -1, right? And 0. And what's a number that's really close to -2 but still to the right of it? That would be -1.999, right? Because -2, okay, right, and the negatives, they're kind of in reversed order, so you got to be careful. To the right of -2 will be a number like -1.9, -1.99. So be careful when it comes to, those negatives. They can kind of mess you up.
Limit from the left means that the reverse.
Exactly, yeah. Okay, the way we denote that we're finding the limit from the right is we have a plus sign in the exponent. So the limit as x approaches c from the right of a function. So again, that little plus sign in the exponent of c, in the exponent kind of place. So a plus sign in the exponent. And then for limit from the left, well, you guys, like Jeff said, you can pretty much figure out it means that x approaches c from values that are less than c. Okay? And you can imagine then, to denote that kind of limit, it'll be the limit as x approaches c, and then for the exponent for c, we'll put a negative sign. Okay? And again, be careful with this one because students, again, can get a little confused here. If you see a negative sign in front of the c, right? If you see a negative sign in front of c, that just means negative c, okay? But if you see a negative in the exponent, if you see the negative sign in the exponent, that means from the left, okay? So just be careful with that. Because if you look at it real quick, sometimes you can mistake what number or what you're trying to do there, okay? Okay, so let's practice with it a little bit here. Okay, number 1, we'll take the limit as x approaches 3 from the left of x squared minus 3x plus 1. Okay, now x squared minus 3x plus 1. Nothing crazy going on here. Okay, it's a parabola, right? Is this function continuous? Are there going to be any jumps, holes, gaps, asymptotes? No. Okay, no problem. So what do you think we can do to evaluate this limit? Since it's continuous, what can we do? Don't need to factor. Just a direct substitution. Just plug it in. Factoring would, if it factors, you could, but it's not necessary. Just plug it in. Plug in 3. I mean, that's all you really need to do here. So it'll be 3 squared minus 3 times 3 plus 1.
Aren't limits usually in impossible numbers, though?
No, they don't have to be. Oftentimes they are because the non-impossible ones are so easy. You just do direct substitution. Or like oftentimes you find limits of like weird situations, not like these kind of things. Because you're right, it's just kind of like very straightforward otherwise. Yeah. But we're just making sure we get that part down too.
But what does a limit exactly mean then?
It's the idea of, again, approaching a particular what happens. So it's kind of two things are being approached, right? In the sense that you are told your x value, your independent variable, is approaching a certain value, a number, okay, a quantity, and then simultaneously to that, then our part is to analyze what happens to the function value as the x value approaches that particular value, okay? So, and then likewise here, if we approach 3 from the right, the exact same function, it's still continuous, right? So it's the same thing. We'll just plug it in. Okay, which I know this might seem obvious, kind of silly that we did this twice, but I mean, this result is necessary. I mean, if our function is continuous, right? If our function is continuous, that means that the function is going to exist everywhere, and the limit must exist everywhere too. Okay, and so if, for example, these two numbers were different, right? If the left-hand limit and the right-hand limit were different, that means the overall limit, okay, for example, the limit as just x approaches 3 would not exist, right? We saw this happen yesterday with the absolute value of x minus 5 over x minus 5. As you approach that 5 from the left, you were at -1. As you approach the 5 from the right, you're at +1. Since the left-hand side and the right-hand side disagreed, the overall limit, we said, did not exist. You could still find the left and right-hand sides, but you couldn't do the overall.
So something like a piecewise function would have that kind of thing happen?
Ah, very good. Yes, we'll be coming up to that in just a minute. So for a continuous function, right, which is what we had here, and most often we see those kind of things, for a continuous function, just use direct substitution. Okay? No surprises there. Just like you would for a no-sided or both-sided limit, I guess we'll say. For a left or right hand only, again, just use direct substitution for a continuous function, or if the function is continuous and around that number. Okay. But now let's start with a new function here, and since Jeff sent something about piecewise, actually it's not because he said that, but it just so happens that it was what we were going to do next anyway. But sometimes it's fun to blame other people. Okay, we'll look at a piecewise function. Hooray! Okay, so let's see some examples here. All right. So first of all, is this piecewise function continuous?
No.
No? How do you know?
Because, well, I didn't actually check, but it's unlikely because one of them's a parabola and one of them's a linear.
Okay. They could still join up, though.
They could join up, and I did not check, but
right.
That is...
How could we check to see if they join up?
Just plug in -1.
Not -1.
Or 1.
Yeah, 1. Yeah, plug in 1. Okay, so let's do that. So if we plug in 1 here to x squared minus 5, what do we get?
-4.
-4. If we plug 1 into 2x plus 5, what do we get?
7.
7. So at 1, and now granted, Mr. Wid, it's x for less than 1, not x equal to 1. I get that, but the idea is we're going to approach up to that 1 there. So we can basically like kind of plug in 1 here, see what this value is. So we got a -4, we got 7. Do these two pieces join up at 1? No. So is this function continuous? No, and specifically it is not continuous at 1, right? Okay, so since it's not continuous at 1, direct substitution here, if we're trying to like evaluate limits around 1 or at that 1, or as we approach 1, something like that, we probably shouldn't use the direct substitution. Well, or at least we'll have to be careful about these things. Okay? So now, that being said, if I was trying to find a limit, as x approaches, like let's say -10, okay? If I was trying to find the limit as x approaches -10, that would be for this top piece, right? Because my x value is less than 1. Is this top piece continuous for all values less than 1? It is, right? This is just a parabola, and it's going to be fine for x values less than 1. There's no problems here, right? And we're not going to divide by 0. There shouldn't be any jumps, holes, or gaps. It's just a parabola for x less than 1. Likewise, if I wanted to evaluate the limit as x approaches +10, right? We'd be looking at this one now because my x value is greater than or equal to 1. And again, this is continuous to the right of 1, right? It's just a line. So the individual pieces for their individual intervals are okay. It's just at that one we're like having a jump, a gap. So yeah.
So that means that the limit at the regular two-sided limit doesn't exist, but the limit as x x approaches negative, x approaches 1 from the left.
Yes.
Would be 7, and the other one would be -4, right?
Okay. Well, so let's see.
Or is it the reverse?
Right. So let's see here. So we're going to find here the limit as x approaches 1 from the left. Okay, which is what Jeff just said there, right? The negatives in the exponent. Again, it's not -1. It's 1 from the left. Okay, of the function here. So which part of the function should we use to approach 1 from the left? The top one, right. And why do we do that, Natalie? I heard you saying it. Yeah, because you have less than 1, right? So if we're approaching 1 from the left, those are from values less than 1. So we're going to use this piece, okay? And then what do? Plug in that 1. So it's going to be 1 squared minus 5, which will be -4. Okay? So since we're stipulating we're only going to approach 1 from the left, for all values that are less than 1, which is approaching 1 from the left, we're going to use that top piece. Okay. How about then the limit as x approaches 1 from the right?
That will be 7.
That one will be 7, right? We're going to use the bottom piece, right? Because the bottom piece deals with x values greater than or equal to 1. Since we're approaching 1 from the right, those are values greater than 1, so we'll use this bottom piece. So 2 times 1 plus 5 is 7. Okay. All right. And so then, what is the limit as x approaches 1 of f of x going to be?
It doesn't exist.
Does not exist. Does not exist. And if you want to justify it, because the limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right of f of x. Okay? That's your justification right there. I don't think I'll ask you to justify something like that, but in calculus, this is a very, very common kind of question you might be asked. Okay? To justify why a limit might not exist, or why something's not continuous, or something like that at 1. Okay? You really shouldn't say, so for example, to justify that it's not continuous, you really shouldn't say, well, the two graphs don't join up. I mean, that's pretty all right for us right now, but in calculus, you're going to want to, this is part of the definition of continuity. So since this is not true, we'll be able to then say the limit does not exist, which means then the function can't be continuous at that point.
But I mean, it's easy to. I think it's much easier to explain to someone why a function is not continuous if you just draw a picture of it.
I agree. But you also have to consider your audience too. In calculus, your audience are calculus teachers, right? People that want you to show that you fully understand something. But to the lay person, absolutely, because most people have an understanding of what continuity means, right? It means not broken, kind of thing, or something like that, or not, whatever. When they see a picture of it, they get it, kind of thing. But for a calculus AP, you want to you can give it a good justification. Yes. All right. I'll give these two here to you. So go ahead, find the limit as x approaches 5, and find the limit as x approaches -5 of this function as well. Okay, so go ahead and take 2 seconds here and do that. Okay, find the limit as x approaches 5 and the limit as x approaches -5. Yep, same function. Okay, Laura, you got an answer for us for number 6?
Yes, got
15. 15. Everyone else get 15?
I got 20.
You got 20? Oh, I think you plugged it into the wrong. It should be 15. 20 is for number 7.
Oh.
20 is number 7. Okay. But yes.
-5, right?
It was -5 for number 7.
Wait, no, I did the problems in the wrong order.
There you go. Okay. So there you go. Oops, I froze it. Sorry. Boop. There you go. Questions on 6 or 7? Easy peasy. All right, flip over to the back. We're just going to do a few one-sided limits now from a graph. All right, so it's, also important that we're able to analyze from a graph. Of course, if you wanted to do a one-sided limit on your calculator, right, for the numeric approach, you would just plug in numbers that were to the left and to the right of whatever particular limit you're trying to do, right? You would only consider the one side. Here for a graph, though, we want to make sure we can do one-sided limits from the graph as well. Sorry about these numbers here. They are kind of tiny, but it is counting by ones here. So if you want to write in some of them there just for your own benefit, okay? So we'll say this function here is f of x, all right, and we'll focus on the next one here in a second. Now, this is the entire graph. This entire graph is f of x, right? Which means we have these two pieces here, and I guess we can assume that it's going to continue on, so we could probably put arrows on the end there too. So this is piecewise, right? We have two pieces, a linear piece and a quadratic piece, but this is all together, okay? It's not two functions.
Linear piece is a point of discontinuity.
Right. This is two functions here. It's not two functions, sorry, it is one piecewise function altogether. Okay, so consider the whole graph as f of x there. Okay? So, yes, let's answer some questions here. Let me move this over. There we go. The limit as x approaches 1 from the left of f of x. The limit as x approaches 1 from the left of f of x. Okay? So any volunteers here? What do we say? All right, Jeff, what do you say? Limit as x approaches 1 from the left. What's that?
-2.
-2. Are we all in agreement? -2. Okay, I saw a head shake, so we'll take that as everyone agrees. -2 is correct. All right, it is -2. Again, here's the x value of 1. Okay, if we're going to approach 1 from the left, to the left of 1, that's this piece of the graph. And so as we approach 1 from the left, so again, we're not moving left, right? We're approaching 1 from the left. So from the left-hand side, we're going to move in closer towards 1. All right, and so -2 is our answer there. Okay, limit as x approaches 1 from the, well, you guys probably figured out what I was going to ask next, right? But from the right, what's this one going to be? -1. Natalie, that's right. Yeah, -1. We're approaching 1 from the right. So from the right to the right of 1 is this piece of the graph. Okay, as we approach closer and closer, -1 is the answer there. Okay. Number 3, the limit as x approaches 1 of f of x. It does not exist. D, N, E for short.
And number 4 is going to be the limit as x approaches -1.
Yes. Sorry.
Number 3 does not exist because the two are at the same points.
The left-hand and right-hand limit of 1 are not the same, so therefore the overall limit at 1 does not exist. Okay? All right, here's some for y'all to try. And Jeff pretty much guessed what it was going to be, or maybe other people did too. But so we'll approach -1 from the left. Okay, find the limit as x approaches -1 also from the right. And then also tell me what the overall limit is as x approaches -1, including whether it exists or does not.
All 3 of them are -2.
Okay. And then also why don't you go ahead and give me f of -1 as well. Okay.
Doesn't exist.
So, all right. Write down what you think it is. All right, we'll see what we get.
4.
Okay. And yes, we will be using that graph in the bottom too. Don't you worry. Don't you worry.
This
Yes, sir.
concept plays
that's good. I would say, though, you might want to check this last one, okay? You might want to check the last one.
-1. It's a pointer just
Look at the entire graph. Look at the entire graph.
I didn't see that.
I know you didn't. Yes.
That's 2. There we go.
Okay. Let's go to Samantha. Samantha, what do you say? Limit as x approaches -1 from the left. -2? Yes, that's right. Good job. All right. How about Brendan? Yeah, -2 as well. Okay. Let's go to someone who's here. Womp womp. Tommy, number 6. What's the overall limit then as x approaches just overall -1 f of x? What do you say?
I did the wrong one.
Oh. Okay. Well, what'd you get for 7 then?
Like,
Oh, you did the bottom one. I see what you're saying. You used the other graph. My apologies. All right. We'll let you slide here. Caitlin, what do you say then? Number 6.
That's the only one I didn't do.
Okay. So why not?
I just didn't do it.
Weren't sure how to figure it out, or you just didn't get to it.
I just didn't.
Okay. All right. Ethan, save us. Number 6. It would just be -2. Exactly right. Okay. In this case, the left-hand limit and the right-hand limit do exist, right? And they are the same, so therefore the overall limit must be -2. Okay. And then finally, number 7. Sorry, let's go to Daniel. 2 is right. Positive 2. Okay. Nice. So, wait, is this a second exam? Oh, this is the exam. I see the word exam at the top.
helps you know what it is.
Yeah. Oh, thinking, Mr. Wood. You're a thinker. Okay. It's because it's early. That's what it was.
No excuse.
Because we're not getting it today. Anyway, so there's the answer. Now, again, this is beyond what we need to worry about for this class, but for those of you going on to calculus, this is a good question too. Okay. Since the limit, so the limit as x approaches -1 from the left, the limit as x approaches -1 from the right, both are -2. The limit as x approaches -1 overall, right, is also -2 as a result, since the left and right-hand limit are the same. But f of -1, f at -1 is 2. Would we say the function is continuous at x equals -1?
Yeah.
Is the function continuous here?
Yeah.
I mean, just think, kind of just think intuitively, right? Our function's going along here, and then whole, and then continues along, right? We do have a value up here, but do we really want to say something like this is continuous? No, we don't. Okay. What's happening here? Well, in order for something to be continuous, another property. So in addition, if you go back to the front, right? On the front, we said the function was not continuous there because the left-hand limit and right-hand limit disagreed, so therefore the limit did not exist. So one way something cannot be continuous is if your limit doesn't exist. Okay, at that point. Another way that something can be discontinuous is if the limit exists and the function exists, but if the limit and function value are different. So here the limit as we approach -1 exists, it's -2. The function at -1 exists, it's +2. But since they disagree, since the value of the function at -1 and the limit as x approaches -1 of the function disagree, then this function is discontinuous at that point. And of course you can see it visually, but for a good justification, what I just said was the justification. Okay, visually, yes, it's easy to inspect and see it, but for a justification, again, if you're planning on taking AP Calculus, and again, you'll get more practice. You'll actually write down the definition of continuity and what it means and stuff. All right, we got 3 more problems I want to do here, and we're going to use g of x to help us with those. Okay, so g of x then is going to be this altogether graph, this piecewise, this linear. All right. So we're going to do the limit as x approaches 0 of f of x plus g of x. The limit is x approaches 0 of f of x plus g of x. Now we do not know what the actual function is for f. We do not know the actual function for g. Could we come up with it? We might be be able to come up with it using like our transformations and stuff like that, but it's not necessary. Okay? To find the limit of a sum, is equivalent to finding the limit of the individual pieces and then adding them together. So in other words, this is the same as just taking the limit as x approaches 0 of f and adding the limit as x approaches 0 of g. Okay? So, what is the limit as x approaches 0 of f? -2. What is the limit as x approaches 0 of g? 3. -2 plus 3 is 1. That's your answer.
Did you use the first one? Did you use the first graph as well?
We had to, right? Because we were talking about f plus g. So we used f's graph to get the limit as x approaches 0 of f, and we used g's graph to find the limit as x approaches 0 of g. Okay, let's do 2 more here. Limit as x approaches 1 from the right of f of x plus g of x all over 3. So yes, we're still talking about f plus g, but the limit has changed. We're no longer approaching 0, but we're now approaching 1 from the right. So we're going to change our values a little bit here. Okay. What's the limit as x approaches 1 from the right of f? Yeah, it should be -1. Okay. What's the limit as g approaches, or sorry, as x approaches 1 from the right of g? It's going to be 1, right? So here's g, right? To the right of 1 is this part of our function, and we're approaching it from the right. So we're going to go, okay? So we're approaching +1 there, and that's divided by 3. Well, -1 plus 1 is 0, divided by 3 is still 0. Okay? Last one here. Limit as x approaches -1 of g of f of x. And here again, we'll kind of like just evaluate it piece by piece here. So what's the limit as x approaches -1 of f? It's -2, right? So this is essentially equal to g of -2 then. What's g of -2? Yeah, it's like -1. I know it is not as quite as clear there. I'd say -1 though, yeah. Okay. So yeah. So again, we just evaluated the limit as x approaches -1 for f, found that value, and then just did g of that value. So g of -2 there. All right. Questions on any of that? All right. So what I would strongly encourage you to do, right, at this point, is to take a look at the Google Classroom. I have posted our homework for tonight.